For decades, Jupiter's core was one of the biggest unsolved questions in planetary science. Was there a solid center buried beneath all that crushing gas? Or was Jupiter so enormous and primordial that it formed without a core at all? A giant ball of hydrogen and helium all the way down? For years, both sides had reasons to believe they were right. Then Juno arrived, slipped closer to Jupiter than any mission before it, and shattered the debate in the most uncomfortable way possible. Because it turns out Jupiter's core is there, but not in the form anyone expected. It is not solid. It is not absent. It is something stranger, something diffuse, diluted, and blurred into the planet around it. A fuzzy core. And once that idea entered the picture, Jupiter stopped looking like a solved giant and started looking like a planet whose deepest layers may be rewriting how gas giants form across the universe. For a long time, two major ideas dominated the conversation about Jupiter's interior. One said Jupiter might have formed directly from the collapse of a gas cloud in the outer solar system. In that view, the planet would not need a solid seed at all. It could have been built like a great gravitational avalanche, pulling itself together from gas until it became the giant we know today. If that were true, Jupiter would not have a dense core. It would be more like a layered ocean of gas and fluid all the way down. The other theory felt more intuitive to many scientists. It said Jupiter likely began with a solid core made of heavy elements, carbon, oxygen, silicon, iron, and other dense materials. That core would have grown first in the colder outer solar nebula, then used its gravity to capture hydrogen and helium over millions of years. This core accretion model fit many ideas about how giant planets ought to form. Build the seed first, then let the gas pile in. The problem was that neither theory could be confirmed cleanly. Earlier missions hinted that Jupiter contained more than just hydrogen and helium. Galileo provided evidence that metallic hydrogen deep inside was probably involved in generating the planet's immense magnetic field. But none of that was precise enough to tell scientists whether Jupiter had a compact core, no core, or something in between. The debate survived because the data never struck deep enough. Until Juno. Juno was launched in 2011 for one reason above all: to measure Jupiter's gravitational and magnetic fields with a level of precision that previous missions could not approach. Instead of circling lazily at a distance, Juno dove in close, following a highly elliptical polar orbit that brought it to within about 4,200 kilometers of Jupiter's cloud tops. Again and again, it plunged over the planet, each pass allowing it to feel tiny changes in Jupiter's gravity. That is the key to the whole mystery. A planet's gravity is not perfectly uniform unless its mass is arranged perfectly uniformly. And real planets are never that simple. If a planet has dense regions, diluted regions, or unusual distributions of heavy elements, those internal differences slightly alter the gravitational field. Juno was sensitive enough to detect tiny changes in its own speed caused by those fluctuations, changes so small they sound almost absurd. By tracking how Jupiter's gravity sped the spacecraft up or slowed it down, and reading those effects through Doppler shifts in Juno's radio signal, scientists could begin reconstructing how Jupiter's mass is arranged inside. What emerged was a shock. Jupiter's interior did not match the idea of a sharp, compact core with a clear boundary, but it also did not match the idea of a completely coreless gas giant. Instead, Juno's data suggested a dilute core spreading across a huge region, roughly half the radius of the planet, blending heavy elements upward into the surrounding hydrogen-rich layers. The neat dividing line scientists had imagined was gone. Jupiter's core looked fuzzy. Once Juno revealed this strange interior, one explanation quickly became popular. Maybe Jupiter started with the kind of solid core that the core accretion model expects. But sometime early in its life, it suffered a catastrophic collision with another young planetary body. That impact could, in theory, have shattered the core and mixed heavy material upward into the surrounding layers, creating the diffuse structure Juno seemed to see. It was dramatic, but it sounded plausible enough. There was only one problem. When researchers tried to model that event, the results did not cooperate. They ran simulations of giant impacts under different conditions, different impact angles, different speeds, different proto-Jupiter sizes, and the same thing kept happening. The collision disturbed the planet, yes, but after enough time, the dense rocky material settled back down again, like sediment sinking through fluid. The sharp boundary reformed. The fuzzy core did not persist in the way Juno's data seemed to require. That failure was important because it took away the need. One catastrophic accident explains everything. Escape route. If a giant impact cannot naturally keep the core diluted over time, then maybe the fuzziness is not a temporary scar at all. Maybe it is something more fundamental, something tied to how gas giants form and evolve from the beginning. And that possibility changes the story far beyond Jupiter itself. The next major clue did not come from Jupiter. It came from Saturn. Researchers studying wave patterns in Saturn's rings realized that those waves are influenced by vibrations deep inside the planet. By combining that ring data with gravity measurements, they concluded that Saturn also appears to have a diffuse or fuzzy core, not a simple compact center and not a fully mixed interior, but a gradient, with heavier materials concentrated more toward the middle and gradually dissolving outward without a sharp edge. That changed everything. Because if both Jupiter and Saturn have fuzzy cores, then this starts looking less like a rare accident and more like a common feature of gas giant evolution. It suggests that our old interior models were too simple. Gas giants may not be built from a clean ball of heavy elements wrapped in gas, nor may they be homogeneous all the way down. They may instead have complex compositional gradients, partially mixed interiors, and large regions that resist simple convection and simple classification. And that is what makes Juno's results so powerful.